Okay, on to section 1.3. We are again going to be mostly looking at covalent bonds, and I want to cover more about the structural identification of covalent bonds, how to properly predict structures using Lewis dot structures, and show where electrons are. So remember that covalent bonds, as mentioned before, involve sharing electrons between two atoms, almost always nonmetals. Atoms share electrons to achieve a more stable electron configuration. So maximum stability is reached when an atom achieves a full valence shell. Remember that the valence shell is the outer shell of the electron, of the atom itself. And when it is filled, the atom becomes more stable. Electrons may not be shared equally sometimes. So there can be things that are covalent bonds that are polarized. An example here, this is hydrogen fluoride. This does not share equally, and you can see that the fluorine actually has more of the electron charge, more of the electron orbital, and the hydrogen has less. So even though it is a shared bond, it's not shared equally. It's not a full ionic bond in which the electron is completely given away to the other element, but instead the density is shifted. So you should have covered drawing Lewis structures, and I want to review this in depth and be sure you really know how to draw Lewis structures, what they mean, and kind of common placements of electrons, because we're going to be doing a lot of drawing in organic chemistry. You're going to be moving on to drawing more complex molecules, and getting the basics of the Lewis structure are really going to help you. So remember that Lewis structures, in these structures, electrons are represented as dots or lines. I prefer that you draw it like this example, in which your bonds are lines. However, you are allowed for Lewis dot structures to complete a structure like this if it helps you understand where the electrons are coming from. We are going to be moving towards structures that look like this in the future. We're going to be doing a lot of line drawing. So get used to the idea that when two electrons come together, they form a bond. So again, the line denotes a pair of electrons shared in a covalent bond. The other electrons that are to the side are not shared. They're not bonding. And we also use atomic symbols if we need to denote atoms that have a positive charge or a negative charge if they have extra electrons. Remember, not all electrons will be involved in covalent bonding, just like in our carbon dioxide here. Some of the electrons on the oxygen are not bonding, and they're just sitting to the side of the oxygen. These are non-bonding, unshared pairs that are just drawn as dots on the edge of the atom. Remember that electrons are localized on a single atom or between two atoms. They're not just floating around randomly. Either they're part of that one atom or they're shared as a bond. So here's an example with our hydrogen. So neutral hydrogen atom needs one more electron to achieve a full valence shell. If you look at the periodic table, the next noble gas at the end of its row, which denotes what its full shell should look like, is helium. Helium has 2 electrons in it. Hydrogen only has 1. So again, it wants to gain an electron to fill its shell. So in H2, the electron configuration of each hydrogen atom looks like helium. You can think of each atom of having that filled shell, although it is shared as a bond. So they each donate one electron, they share those electrons. Sharing the two electrons equally gives them equally a full shell. The sharing of these electrons can also be drawn as a line. What about in fluorine? Similarly, a neutral fluorine atom needs one more valence electron to achieve a full shell. In this case, fluorine has 7 valence electrons, but if you look at the periodic table, at the end of the periodic table, the next noble gas has 8 electrons in its shell, meaning that fluorine needs to get to 8 to fill its shell. So here, fluorines will each donate their 1 extra electron to a neighboring fluorine to be analogous to neon, the second noble gas. The donated electrons form a covalent bond that allows them to form a bond which can be drawn as such. Now, in this case, each fluorine has a lot of non-bonding electrons. All of these other electrons did not participate in the bonding. And so they are drawn in to the side around the fluorines. Now, we have something called the Octet Rule. This is a rule. It does not apply to every single molecule, and so we say this with caution, but it will help you to remember that generally for second row elements, a full valence shell is going to contain 8 electrons. It has 1s, 1 or 2 p's of the x direction, 2 p's of the y direction, and 2 p's of the z direction, ultimately adding up to 8. And so because 8 is the max at this point, we call it an octet because it contains 8 electrons. So generally, a stable molecule in second row atoms are going to share electrons until they achieve an octet. And when checking that the octet rule is satisfied, double count shared electrons once for each atom involved in sharing, meaning that in this case, fluorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And we're going to count those shared or bonded electrons for the second fluorine. And it also has 1, 2, 3, 4, 5, 6, 7, 8. So it has a full octet of electrons. Let's do some more examples of Lewis structures. Another way to think about how many bonds an element will make has to do with how many unpaired electrons it has. Let's start with water. What I like to do is draw the elements out individually first. In this case, we have 2 hydrogens and 1 oxygen. So draw the Lewis structure of each of the elements individually. We know that hydrogens have 1 electron. Here's 1 hydrogen, and here's a second hydrogen. Oxygen has 6 electrons. When drawing the electrons around an atom, you're going to individually draw electrons until you reach 4 first. So 1, 2, 3, 4. Once you reach 4, you're then going to start pairing until you reach the number of electrons that that element has. So in this case, 5, 6. So you see again, in this way, if you do it this way, you will always draw the number of bonded electrons or non-bonded electrons paired together. In this case, for oxygen, these electrons and these electrons will be non-bonding. Anything that is left alone by itself will be bonding electrons. So in this case, you can see that there are 2 bonding electrons. That means that oxygen will form 2 bonds. This is something I really want you to remember. Always, always check. Neutral oxygen that's not charged in any way, will form 2 bonds. It always wants to form 2 bonds. If your structure has an oxygen forming 4 bonds, or 8 bonds, or 3 bonds, it is wrong. Oxygen likes to form 2 bonds. Hydrogen, you can see here, likes to form 1 bond. Okay, so putting these together, I know my oxygen has these 4 electrons that are non-bonding, and it's going to want to form 2 bonds. And I have 2 hydrogens, and they each will form 1 bond, making a structure like this. So there is my Lewis dot structure for water, H2O. Now let's try another one. Methane. This involves carbon. This is CH4. Carbon, we look at its number on the periodic table. It's valence electrons. It has 4 valence electrons. So I'm going to do the same thing I did with oxygen. Each electron singular until I get to 4, and then pairing after that. In this case, there are only 4, so 1, 2, 3, 4. So I will stop. And then I have 4 hydrogens. So based on what I said before, how many single bonds will carbon want to make? There are 4 non-bonding, or excuse me, 4 unpaired electrons here. So it will make 4 bonds. This is another key thing I want you to remember during your time in organic chemistry. Carbon likes to make 4 bonds. If it is a neutral carbon, it's not charged. In an abnormal situation where it's charged, etc. It's a neutral carbon, a regular structure, it will form 4 bonds, not 6 bonds, not 2 bonds, 4 bonds. So in this case, we have a carbon, 4 unpaired electrons, excuse me, and 4 hydrogens that each want to form 1 bond. Oh. There is your Lewis dot structure for methane. Okay, and last, we will do hydrogen chloride. So again, we'll look at your periodic table, figure out how many valence electrons these have. Hydrogen has 1 valence electron, and chlorine has 7 valence electrons. 1, 2, 3, 4. I'm going to start pairing. 5, 6, 7. Okay, so in this case, chlorine has 3 sets of electrons that are non-bonding, and it has 1 that is bonding. It will form 1 bond. Hydrogen also will form 1 bond, so we know that this structure should ultimately look like this. The line here for the bond. Okay, so make sure you practice these Lewis structures. Understand how many bonds things will form, as in the examples we had here. Remember, to be able to solve how many valence electrons, I've just been counting them out here, but if you're unsure how many valence electrons something has, make sure to look at your periodic table. It should be how many electrons are in that last row up until that element. Okay, but we've done a lot with the single bonds and Lewis dot structures, but we will also be looking at multiple bonds, things like double bonds and triple bonds. So more than 2 electrons can be shared between an atom, and often this is necessary to satisfy that octet rule. So when 4 or 6 electrons are shared, you have this multiple bond. A double bond is when 4 electrons are shared. So 2 and 2, as you see in this example here. And a triple bond is when 6 electrons are shared, or if you have 3 sets of 2. That is a triple bond. So to draw a Lewis dot structure that has a double bond, here we have ethylene. This is C2H4. And ultimately, we must share 4 electrons between the carbon atoms to achieve an octet. You can see if I did not share 4 electrons, as in the example here, you would have 2 of those electrons that want to form bonds left over, not making a bond. And so those will share with each other, making this 4 electrons that are shared here and making a double bond. Now, in my example I gave before, I talked about how carbon always wants to make 4 bonds. How can I reconcile this with these double bonds and triple bonds? Well, you count the double bond as having 2 bonds. So in our case of ethylene, carbon here is forming 1, 2, 3, 4 bonds. So to double check your work, like I said, carbon always wants to make 4 bonds. And so a double bond will count as 2 bonds. Triple bonds similarly work as the double bonds. To draw a Lewis structure of ethine, C2H2, you have to share 6 electrons between the carbon atoms to achieve an octet. So in this case, our carbon, remember, on each wants to make 4 bonds. We only have 2 hydrogens. They can only contribute 1 bond. So you have these 3 electrons left that all want to form bonds. A triple bond acts as 3 bonds. This is a way that you can think about forming a triple bond. And redrawn cleanly, it looks like this. Ethene has 1 triple bond in which it is sharing its 6 electrons, and then a single bond of each carbon to a hydrogen. So ultimately, each carbon still is forming 4 bonds. This carbon has 1, 2, 3, 4 bonds, and the other carbon has the same.